right, so to begin, I'd like to acknowledge the co-authors of this presentation, Martin Robards, who we heard from earlier from the Wildlife Conservation Society, Jerry Galt and Ren Hansen from a company known as Gen West out of Edmonds, Washington, my partner in crime at ABSI, Aaron Poe, and Ben Matheson, who's also working with us at the Fish and Wildlife Service. So since I'm actually giving this presentation in the Aleutian Islands, I think this might be the only time I've ever done it, those of you who live and work here and who boat in the Aleutians, you look at this picture and you say, yeah, that's what it looks like on a nice day. This is what it looks like on a bad day. And I'm sure that you've all been there too. You know, I was looking at this picture last night and I realized that guy right there, he kind of looks a little like Jeff Williams. I don't know, maybe he's his great-grandfather or something, but it was rather striking. So we already heard from Commander Hobby about the Northern Great Circle Route. What's a Great Circle Route? Well, it's the shortest distance between 2 points on a sphere, such as the Earth. So the Great Circle Route from the Pacific Northwest, say Seattle, to a port in Asia like Tokyo, it goes right there. And if we zoom in a little bit, you see that it tracks through Unimak Pass on the eastern end and Buldeer Island, next to Buldeer Island on the western end. That's the shortest distance. And it was on this kind of a route 11 years ago that this vessel, the Selendang IU, was traveling when it developed some difficulty, and it was driven by strong winds and high seas, and it drifted south, ran aground here on Unalaska Island over by Makushin Bay, broke in half, spilled something like 400,000 gallons of heavy fuel oil, 50,000 gallons of diesel fuel, its entire cargo of soybeans, and I guess you know, when you have 3 feet deep soybeans on the beach, that's something to contend with as well. It oiled something like 86 miles of shoreline, killed thousands of seabirds, a handful of sea otters, and 6 of the crewmen, while they were being rescued by the Coast Guard, the helicopter was struck by a wave and went into the water, and the Coast Guard folks got out because they were prepared, they were trained, they were equipped. The crewmen perished. So when you look at this sort of a thing, this is another example of what it looks like on a bad day. About the only way it could have been worse would have been if this was a tanker carrying crude oil. And partly in response to the Selendang IU, the Marine Exchange of Alaska has built a network of AIS receivers around coastal Alaska. For those of you who aren't familiar with the term, AIS stands for Automatic Identification System. It is a system that is required by the International Maritime Organization for all vessels over 300 gross tons. And basically the way it works is you've got this transponder on a ship, and it's getting the location by a GPS, and then it is sending out a signal that also, in addition to having the position, it has information about the vessel. It's here I am, here's who I am, here's where I'm going. And then that signal initially it was picked up by other transponders on other vessels or by shore-based stations like we saw in that map of the Marine Exchange of Alaska. And more recently, in the last 6 years or so, there have been satellite constellations that have been deployed that can also receive these signals. So they give you a much bigger coverage of the entire world. So to give you an example of what this looks like, this is a time lapse of the Marine Exchange of Alaska's site where you can watch in real time when the vessels are close enough to one of those shore-based stations. You can watch these things motor along in real time and see where they're going. And then if you wanted to, you could select something like that ship there, and you can get more information about it. This system, the Marine Exchange of Alaska, that is available for a subscription fee where you can actually get a username and password, and you can log in and look at this. And I can assure you that folks at the different vessel traffic organizations and the Coast Guard, they are watching this all the time. So based on that those land stations, in 2012, there was a report prepared on the vessel traffic through Unimac Pass. And what we see in this figure was there was about 4,500 transits that went through Unimac Pass, about 2/3 of them going westbound, about 1/3 going eastbound. There was a smaller amount of traffic that they were able to detect that passed south of the Aleutians. And then what the other point to recognize there is out west, you see where the lines get kind of hazy. That's because the furthest most station in the Aleutians is in ADAC. So once the ships are west of that, they literally drop off the radar, or in this case, AIS. And so that's why a few years ago, our partnership at the Aleutian Bering Sea Islands LCC, we purchased an archive, a 3-year archive of satellite AIS data. It's about 72 million vessel locations for our region, something like 45 gigabytes of data. And when you put it all together and do what we call a heat map, you get a sense of where all that traffic is going. And in this case here, the brighter colors are heavier areas of traffic. And so to give you an example of what we can do with that, here's a map that shows the major passes between the Bering Sea and the North Pacific. And what we're seeing here is that there was more traffic in 2012. So for example, in Unimac Pass, there was something like 4,850 vessels in 2012 versus 4,000 in 2011. So that may have had something to do with the recession, kind of recovering from the recession. We're not really sure all the reasons behind that. We can also see that similar to what they found for the land-based work, most of the traffic is westbound. Okay, you got about 2/3 of the traffic. The blue bars are the westbound traffic. So you got more westbound traffic through Unimac Pass, and you've got more westbound traffic out there by Attu Island. And lastly, that southern route there seems to be more predominantly eastbound. So what we think is probably happening is ships may be going from North America to Asia through the Bering Sea, and then some of them at least are returning along that southern route because they've got to come back somehow. And just to give you some more confidence in this information, all of the data has been reviewed by my border collie. His name is Wiki the Wonder Dog because sometimes I wonder why I got this dog. But he does come in handy. Now, of course, we're not really so concerned about the islands as we are about the resources that are there. That's what we're really concerned about. So in this case, if we look at stellar sea lions, which are endangered under the U.S. Endangered Species Act, here we have the major routes that we've identified from our data, and we've got the sea lion haulouts and rookeries. This is where the vessels used to go. And if we measure the distance to the closest route, we get a graph that looks like this, which tells us that about 7,100 sea lions are at haulouts and rookeries that are within 50 nautical miles of a major shipping route. And when you look at the total number, that's more than half of all the stellar sea lions in the Aleutians. And as Lieutenant Commander Hobby mentioned, based partly on our work and largely on their efforts, they applied to the International Maritime Organization to establish 5 areas to be avoided in the Aleutians. It's the shaded area here. There are 50 nautical mile buffers around the Aleutian Islands with 4 passes that are cut through them. And so if we alter the routes to look like that, to stay outside of the areas to be avoided, one of the nice things about that is because of the overall distance, about 4,400 nautical miles, this small alteration in the voyage adds a fraction of a percent to the overall. Wow. Fraction of a percent to the overall distance and time that it takes to travel this route. And so now if we redo those measurements with the new routes, and again, that's where the old routes were, so you have those for comparison, what we see is we've cut the number of stellar sea lions within 50 nautical miles of a major route. We've cut that by more than half. And the difference between these two graphs is actually a representation of the overall risk reduction, which is something like 21%. So you're asking mariners to go a little bit further out of their way for a pretty appreciable reduction in the risk to stellar sea lions. Now, you might be thinking, what about the cute animals? We can also do the same calculation with sea otters. This is some data from the U.S. Fish and Wildlife Service. There's a lot more sightings, but you can measure the distance. You can do it from the old routes and the new routes, and what you get is something that looks like this: 1,300 within 50 nautical miles. Now we cut the number of sea otters to about a third, and that is about a 22% reduction in the overall risk. So again, we're asking, it's asking mariners to go a little bit further out of their way for a fairly, substantial reduction in the risk to these resources. And you might be asking, well, are they doing that? Well, this is some data of bulk ship transits out by the end of the Aleutians. You can see Attu Island, Baldir Island, and the yellow lines are the vessel tracks from November 2015. You can see a lot of them are tracking pretty close to the red lines, the old routes, and they're plowing right through those areas to be avoided. This is December, this last December, and these areas to be avoided took effect on January 1st. Wait for it. That's January 2016, February, March, and April. So it looks like these areas to be avoided are in fact being avoided, and we think that that's going to help reduce the overall risk to these islands and the resources that live there. Now, one of the things that we've been talking about, though, is using distance from the routes to the islands to the resources as a proxy for risk. But as long as the vessels stay under power and go where they're supposed to be going, bad things don't really happen. So what we've done is we've taken our investigation a little bit further, and we've looked at where are these vessels likely to go if they do lose power and they do go adrift. Where are they going to run aground? So we took these 4 major routes and we divided them up into what we call release sites, different release sites. And so this simulation model, we've got the 4 major routes, we've got 21 release sites, 4 seasons. We did 250 random starts of date and time, and we used 40 pseudo ships. I'll explain what those are in a moment. And that comes up to 3.36 million vessel trajectories that we analyzed in this simulation. We used the GNOME model, which is developed by NOAA. Our partners at Gen West did the configuration of the model to simulate a container ship. And we used wind and current data that was developed as part of the response to the Japan tsunami marine debris. They wanted to see where that stuff was going to go. We were able to just get that off the shelf and use it to push our ships around and see where they might go. So this is how the GNOME model works. If you pick a release site like this, at time step 0, you drop in a ship and you apply a current to it and then a wind to it. And the wind actually has a bit of uncertainty around it. You don't know exactly how far the wind is going to blow it down that vector, and you also don't know the directionality. So you've got this sort of an area of uncertainty. And then what you do is you just move your ship into a randomly selected coordinate within that zone of uncertainty. But to get an idea about the overall uncertainty of the model, you do this repeatedly with a number of pseudo ships. So in this animation, we're only going to show 6 because we don't have all day. And once that's done, after time step 1, you've got a distribution that looks something like that. And then what you do for time step 2 is the same thing. You apply a current and a wind with some uncertainty. You apply it to each of those pseudo ships. And eventually the dispersion gets to the point where the pseudo ships are being acted on by different winds and different currents from the model. And we get a sense of where are these things likely to go. And so that would be the end of time step 2. So this is on to our actual data. This is Route 3, Site 10, Winter Simulation 1, which I think was set for January 2nd of 2011 at 3:20 p.m. Container ship at this point in space and time loses power, goes adrift. Day 0, day 1, so you can see the winds and currents are heading south. And then on day 4, it kind of stalls a little bit. Day 5 changes direction. Day 6 starts running aground on Atka Island. And so we'll just let that go one more time so you can see it. We have 40 pseudo-ships, and this gives you an idea of where might that ship have gone if it had gone adrift at that place at that time. And of course, that's only one scenario. That's only one set of winds and currents from the model. We did 250 random start dates and times for each season, and then we rolled those up into what we call an ensemble. So here's the winter ensemble from the same location. Boom, that's day 1. You can see they start running aground as quickly as day 2, and some of them are leaking through the passes into the North Pacific, not hitting anything. And at the end of day 7, we have 21.4% of the pseudo-ships running aground from that location. So let's just let that run one more time so you can kind of get a sense of it. I thought was really interesting was after day 7, the range goes all the way from Buldir Island to Unalaska Island. I mean, they can pretty much run aground almost anywhere in the Aleutians from that point. Okay, so that's one location. Now we can look at things over an entire vessel route, in this case Route 3. And what this graph shows you is that the highest probability of vessel groundings after day 1 are from release sites 1 and 2, which are right close to Unimac Pass. Really no surprise there. The closer you are to land, the higher your chances of running aground would be after only 24 hours. But you can see out there in the western Aleutians that there's a couple of small blips there of I think it's release sites 18 and 16, which are close to some of the islands there. After 3 days, your probabilities of running aground are higher naturally, and then after 7 days. And so what this graph tells us is that pretty much from anywhere on that route, you've got a probability after 7 days of running aground if you go adrift. The probabilities being highest in the winter, and the probabilities being highest in the eastern portion of the route. And we can do that same analysis for Route 4, which is closest to the central Aleutians, and you get similar results that kind of make sense. They're telling you that your probability of running aground is highest in the winter and the fall seasons, and highest in the central Aleutians. Okay, so again, what we've done there is we're looking at the risk of vessels that are traveling on these routes, but as the raw data shows us, they don't always go on those routes. They go all over the place. That may be the most preferred route, but literally the ships can go anywhere. And so the next step of the analysis that we want to do is we want to do it over a grid system like this, and then we can develop what we're calling risk contours. Now this is just a distance buffer, but it kind of illustrates the concept that we could identify where are the areas that a vessel has a high probability of running aground after 1 day. So where are the areas that you really want to exercise caution all the way out to out to 7 days, and then we can look at what are the vessels doing? Are they behaving the way they should be in the areas where there's the greatest risk? We can also roll up those ensembles where the vessels run aground, and we can identify which islands are probably at highest risk to vessel grounding. So that's where we want to take this analysis next. Of course, the whole idea there is we want to avoid having another bad day that looks like this, a container ship that's heading towards the rocks. I want to thank you all for your time, and if you have any questions.